Okay, so welcome to everyone that's here in person, and then welcome to everyone that's online. So today we have Tyler Cowan. Tyler graduated from Columbia University in 2018 with a bachelor's and master's of science in applied physics. He's worked at GISS on Mali development since late 2018. Outside of his work here, he's been learning about quantum computing, ranging from courses at MIT to hackathons and open source contributions. And he's become really a passionate enthusiast on the subject. So he's used IBM's quantum computers for experimental runs as part of his work with the Quantum Open Source Foundation. And I don't know about you guys, but I'm just really excited to learn what all that means. So please join me in welcoming Tyler.
Hey, thank you. So hello everyone. Thanks for joining me. Just want to get a.
Can I cut you off for
Yeah,
a second? Can you share your screen with the WebEx? I realized that was the last thing we were missing.
You know, I can. I actually can.
Yay. Okay.
How's that look?
We see that here.
Okay, cool. So, I just want to get a little show of hands, like, who knows anything about quantum computing? Has anyone heard of it? Anyone understand? Any experts that I have to like not take questions from? So yeah, it's something about that we read about in the news a lot. You know, here are some of the headlines that I've seen in the last couple of years. There's a lot of hype around quantum computing, so it isn't really clear to a layman what's actually going on. And so during this talk, I just want to give a very broad overview from mostly a software perspective, not so much a hardware one, on how quantum computers work and what they might offer us if ever they are commercially applicable. So here's some things we'll be talking about, just how quantum computers can help tackle some algorithmically complex problems. We'll be talking about the qubit, which is the quantum analog of a classical bit, such as zeros and ones that we know very well. And then a short demo using Qiskit, which is an SDK developed by IBM, which we use to interface with quantum computers. So, algorithmic complexity. I think this is something a few of us have encountered before in classical computing. We typically classify algorithms based on the resources they use and how these resources grow as the size of the input grows. So for instance, if we're just adding two numbers that are of the same length, we would expect that the computational resources will scale linearly as the number of digits in those numbers increases. If we are guessing like the pin to someone's iPhone, as the size of the pin grows, it requires exponentially more resources to get the correct password. In general, something with exponential complexity, we kind of classify as a bad algorithm because as the size of the problem grows, it can grow to become intractable. Even using today's supercomputers, there are a lot of algorithmic problems that can't really be solved in a reasonable amount of time. Moving on somehow. Here we are. So before we dive into the specifics, I just want to give one example of a quantum algorithm that kind of kicked off a bit of a quantum computing revolution in the 90s. It's known as Shor's algorithm, and we use it for something called integer factorization. So, if I give you the number 2000, we can all pretty much quickly come up with the factors for it. So for instance, 2 and 1000. But what happens if the number is, say, 200 digits and its factors are both prime numbers? So this is might seem a little abstract, but RSA, which is a crypto system that we use to encrypt almost all the information we encounter on the internet and in our financial systems, relies upon the fact that this is actually a very difficult problem to crack using a classical algorithm. In 2020, scientists factored a 250-digit number that had 2 prime factors, and it took 2,700 core years using a supercomputer. For instance, a number that's 3 times as large using Shor's algorithm with an ideal quantum computer, which doesn't exist yet, you can do a much bigger, solve a much bigger problem in a fraction of the time. On a classical computer, it would take multiple times the age of the observable universe to crack a 617-digit integer factorization. So I just want to tee up that these are the kind of problems that quantum computers are meant to solve. They're not necessarily intended to replace classical computers, but for specific problems that are completely intractable classically, a quantum computer might be able to help. So what we're in now is basically called the NISQ era. It stands for the Noisy Intermediate Scale Quantum Era, which we'll learn a little bit more about as we go through. Essentially, what noisy means is that the qubits, which are the fundamental unit of information in a quantum computer, are very susceptible to the noise in our environment, like thermal noise or radiation. And because of that, it's actually very hard to scale the number of qubits to be high enough to be used for something useful. A decade ago, there were quantum computers with only less than 10 qubits. Now there are some quantum computers with hundreds of qubits, but we would need hundreds of thousands or actually millions of qubits to actually do something useful. So this is very much experimental technology. Quantum advantage, or what some people call quantum supremacy, has not really been demonstrated by anyone. And so you can kind of see here that on the integer factorization problem, quantum computers are only just catching up to traditional computers. This is another algorithm that's kind of famous. It includes, it's used to do searching through an unstructured database, and the speed up for it is, you can see here, you can do it in square root time rather than linear time. So, search is used in almost everything we do today, and so this would have very wide sweeping implications. For those familiar with, P space and NP space, the space that quantum computers are able to efficiently solve is not yet fully determined, nor do we even know if P and NP are distinct classes of problems. But what you can see here, the most interesting part is that there's a class of problems which are efficiently solved by classical computers, and then a class of problems that are efficiently solved by quantum computers. Interestingly, both types of computers can all solve, in principle, the same class of problems, but not the same class of problems efficiently. And efficiency essentially determines whether or not we can do it. Again, if something takes, a billion years just to actually solve classically, that's never going to happen. But it was very shocking to me when I first learned about quantum computing that these two types of computers can all, in principle, solve the same set of problems, just with different levels of efficiency. So you're probably wondering, what actually is a quantum computer, though? We won't be focusing too much on the hardware, more so some of the theory behind it, and the software we use to interface with them. But essentially, quantum computers differ from classical computers, like our phones and laptops, because they can exploit 3 quantum phenomena that have no classical analog, known as superposition, entanglement, and interference. And we'll go through all 3 of those with examples later on. So quantum computing basically began in the early 20th century, along with the, sort of the end of classical physics and the quantum revolution. The EPR paradox was a concern to Einstein because it suggested that we might be able to do faster than light information transfer using quantum physics. That kind of set off a whole century of debate, and only as of a few years ago can people like you and me actually access real quantum computers through the cloud. So they actually exist, they just don't have a ton of computational power yet because they're still kind of small and noisy and inefficient. So on a very broad level, how does quantum computing and classical computing differ? The most important difference that I'll focus on is the fundamental unit that we use to do the computing. So in a classical computer, we use bits, typically using transistors, which take on the values of 0 and 1. And that's the whole story. For a qubit, which is the quantum analog of a bit, hence the name, we can represent the states of 0 and 1 simultaneously, which is pretty unintuitive, but I like to think of it as a coin flip. So when you flip a coin, while it's in the air spinning, it's ambiguous as to what state it's in. It's not really in 0 or 1. And then when it lands and we measure it, we find it's either in 0 or 1. And so it takes a little time to get used to the physical intuition behind that. But in nature, we find that there are states that are not represented with a binary until you measure them. One of the core principles of quantum mechanics, which is not perfectly well understood, is called the observer effect. And measuring a quantum system has a tangible effect on its state. There are other differences that we will not focus too much on for now, but we will come back to that.
Sorry, just why does the computing capacity increase exponentially?
So I'll explain it in a little bit more detail, but essentially, let's say you want to describe a classical system with n components or degrees of freedom. You can describe it with n bits in principle. However, if you want to describe a quantum state, you have to keep track of 2 to the n complex amplitudes. This is because, let's say you're considering like a photon of light. It has a horizontal and a vertical polarization. And so there's 2 complex values that a photon can in principle store within it. Think of it also like, you know, the hydrogen atom. If you have an electron in the ground state or an electron in the excited state, if it's somewhere in the middle, you can't really store the information that contains that state as just a 0 or a 1. You need a complex amplitude, which is a more complex surface in something called Hilbert space that I'll touch upon a little bit. But this computing capacity essentially underlies the core promise of quantum computing, that classical computers cannot effectively capture all the information that quantum states can. So the qubit. Down here, what we're looking at is you know, a representation of something called a transmon, which is one of the leading like physical modalities of what a qubit actually looks like. On the right, we have the block sphere, which, you know, if you continue learning about quantum computing, is something you'll become very familiar with. The block sphere is used to represent what's called the quantum state of a qubit. A quantum state basically encapsulates all the information we could ever know about any quantum system. So the best way to think of it is a 2-level quantum mechanical system. When you think of classical bits, 0 and 1, you kind of get a sense that there are 2 levels to that, but there's no sense of transition between them. It's either a 0 or a 1, independent of whether or not we're measuring it. A qubit, however, can exist in something called superposition, which has no classical analog and is kind of unintuitive. But essentially, it can exist in some kind of state that before you measure it, it is probabilistically going to be 0 or 1. So for instance, a qubit in a certain state could have a 25% chance of being in state 0 and a 75% chance of being in state 1. And until you measure it, you can't in principle know that. Upon measuring a qubit, you get a classical bit in principle. I'll elaborate more. So up here you can see an interesting diagram sort of showing the 2 schematics for a classical bit versus a qubit. On the left, you have 0 and 1. There's 2 options, that's the end of it. On the right, we have the block sphere, which is the diagram we looked at earlier, which is essentially a 2D surface forming a sphere. And these vectors coming from the center rather, which are all the same length, they point to somewhere on the surface, and every unique point on the surface is a new state that a qubit can actually represent. So without going into too much detail, because it can be a little maddening if you're just getting used to it, you can imagine that there are infinitely many points on the surface of this sphere, which means that we can represent, in principle, infinitely many different states, only one at a time, with a qubit. So we'll get a little more accustomed to this representation as the presentation draws on. But essentially, you can see here, there's still 0 and 1 at the poles of the block sphere. And let's say, for instance, this vector, which points to somewhere on the equator of the block sphere, it gives us this state. And we'll go through a bit of linear algebra shortly. But essentially, this state has a 50-50 chance of being measured as 0 or 1. And we never really observe the superposition. We only observe the final classical state. So, stay with me. Just a couple more, physical intuitions. In two classical bits, you can have either, there's two states essentially you can represent. In a quantum bit, in principle, you can store more information than a classical bit because it's probabilistic and not deterministic. If you have a qubit and you measure it once, you'll get a 0 or a 1 with some probability. And if you repeat that experiment multiple times, you can eventually form, say, like a probability distribution showing, a third of the time we got 0 and 2/3 of the time we got 1. I really like the coin flip analogy. It's not really quite correct, but it's sort of it's a good place to start. Think of a qubit as a coin in midair right after you toss it. Is it 0 or 1? We can't really know. And you can't measure it in that state because it's not accessible to us. So, a little more physical intuition. For instance, I don't want to get too much into the hardware, but there are multiple ways that a qubit can be realized. And so there are many ways that a quantum computer can be developed, using either electron spins, which are either spin up or spin down before we measure them, electrons in a hydrogen atom, determining if it's in the ground state or the first excited state, or the polarization of a single photon, depending on its...
Is the photon's polarization quantized in the same way as like an electron state or spin?
It's definitely quantized. I'm not sure if it's an exact analog to the spin, but it is quantized, yeah. And so you get the sense that in nature, there's a lot of two-level systems that are quantum mechanical, that are kind of hard to describe. They're kind of hard to intuit in between these two states. But in principle, they can actually exist, at least we find experimentally, in between these two states. And so a classical computer can't really represent what's going on in a hydrogen atom. We have to make certain approximations, which we'll get into more later. So, not to bash everyone over the head with too much linear algebra, but linear algebra is the language of quantum mechanics. What we see here in this first equation is what's known as, this is the way that we can represent the state of a qubit. So you'll notice that 0 and 1 are retained from the classical bit. Alpha and beta are complex probability amplitudes. And they're subject to the normalization principle such that you have to measure the qubit in either the 0 or the 1 state. So these have to sum to 1, or the squares do anyway. So what does that mean? Actually, how can we possibly use this? So for instance, after measuring a qubit, it will collapse, which is a little ontologically questionable, but you'll find it in either the 0 or the 1 state. And so we use this formalism of vectors to describe the state of a qubit. The 0 state we describe with this two-dimensional vector, or one-dimensional size 2 vector, and the 1 state we describe with this vector. And so you can get a sense that if alpha was equal to 1 and beta was equal to 0, this would perfectly describe the state of a qubit that is in state 0. These could also be, this could be 1 over rad 2 and 1 over rad 2, and then that would mean that there's a 50-50 chance of finding the qubit in either state upon measurement. So you don't have to get, if you don't want to, follow the linear algebra too much, it's not super critical right now. But if you want to learn more about quantum computing, eventually you have to. Here's another example of a single qubit state written in this format. And this is called bracket notation, I guess bracket. You can see here that we're describing the state of this qubit, or really any quantum mechanical object. You can see here that we have two, this is alpha and this is beta. These are complex probability amplitudes indicating what is the likelihood that we will actually encounter a qubit upon measurement in either of these two states. And so you can see they can be complex. This is I over rad2. This is 1 over rad2. If you square them and add them, they sum to 1, because the qubit has to be in some state that we can in principle measure. Bear with me. So before we proceed to a demo and how we actually might use a quantum computer, I wanted to check in and see, are there any questions, anything that really is not making sense that might prevent you from appreciating the actual use of a simulated quantum computer?
Well, so far you haven't described why the quantum bit is any better. Because you've got your linear algebra encodes the ones and zeros,
Yes.
but where do we get any more than ones and zeros?
So
Any more bits?
I'm going to explain. So it's really interesting. The information that's stored in a qubit is not necessarily the information that we can actually extract from it. Qubits live in something called Hilbert space, where we can't actually necessarily access all at once every possible state that a qubit can be in. So why am I saying all this? The information that a qubit stores is not 0 or 1 after you measure it. The information that it stores are these two complex probability amplitudes. Okay. And so for each qubit, there's not one unit of information that's being stored. There's actually 2 units of information. It's both of these complex probability amplitudes that are being stored. And so in principle, when we look at the surface of a Bloch sphere, there's infinitely many states that the qubit can actually be found in. But in order to fully describe the qubit state, a 0 or 1 is insufficient. And so even though after measuring a qubit, we will get a 0 or a 1, we can actually, before measuring, have the qubits interact and apply something called quantum logic gates to them, which will then change their state in a way that's useful to us. So we do the algorithms before measuring it. Unlike with a classical computer, you can just measure it at every single step and check what's going on. With the quantum computer, you can't even really observe what's going on in the qubits until the experiment is completely done. Otherwise, you'll collapse the superposition, and it'll act more like a classical bit than a quantum bit.
So does that mean that you always have to take multiple calibrations in order to sort of actually know what that state is, since only a single evaluation will just give you a 0?
Yes. So in fact, you have to do it tens of thousands or even millions of times in order to get statistical significance. If you measure a qubit one time and you get a 0, you've not really learned anything about it, because you have to do it many times. And if you find that over time, after you accumulate many different runs, it seems like there's a 50-50 chance of being in state 0 or 1, that would indicate the actual quantum state you're working with.
So we have one question online. Are you willing to also take another question now?
Oh yeah, of course.
Okay, Kostas, if you want to unmute yourself.
Yeah, thanks. So I have 2 questions. One
Sorry,
is-
Kostas, just hang on a second. We need to increase the output volume here.
Okay.
While he's asked, or while that's being raised, you said that you square and sum those numbers and you get 1. Square and sum those numbers when you get 0. Maybe I'm bad now.
The absolute value of the squares. Yeah. That was just me not being precise.
Okay, Kostas, go ahead.
Is it better now?
Yes, much better.
Okay. So I have 2 questions. One is, they are more higher level, I guess, in terms of practicality. So one is, if the quantum computers are so much better, then which are real cases where they are not? And my other question is whether they are any good for big data analysis, because big data analysis is not only crunching the data, it's also reading the data from disk and writing data to disk. So how good are they there, or is this an irrelevant question?
No, it's very relevant. The first question, in principle, it's not fully understood if there's a quantum algorithm that is as efficient as every classical algorithm. So, we've been working on classical algorithms for a long time, and so we have many more efficient algorithms that would not make sense to run on a quantum computer. Quantum computers, because you have to operate them at cryogenic temperatures. It's unlikely that we're going to be using quantum computers in our laptops or phones. And so any computational task that you want to do on the go and not use something that's the size of a room, you're unlikely to use a quantum computer for that. So the limitations for quantum computers currently have a bit to do with sort of the nascency of like the study of quantum algorithms and also the difficulty in scaling the number of qubits to something efficient.
So what you are saying is that it is not a question of the problems that we want to solve, but rather than the practicalities of it and also the fact that we don't have the efficient algorithms yet. But in the distant future, one can envision that if we have all the same algorithms efficiently written for quantum, then they should be superior for all scenarios, right?
In principle. I think it's currently an open question. Even though they can both tackle the same set of problems, it might be that the actual physical operation of a quantum computer, even from like an energy perspective, is more inefficient compared to a classical computer. Having to use, having to cool things down that cold and have it be this isolated from noise and vibrations. It might not actually be worth the overhead for certain applications. I envision quantum computing more acting hand in hand with classical computing. And there's actually a whole class of algorithms which are hybrid quantum classical algorithms, which are used for like chemistry simulation, for instance. Yeah. And as for your big data question, a lot of people are very excited by the big data potential of quantum computing. There are, some issues with data loading into quantum computers that I'm loosely aware of. My understanding of, essentially is that because you can encode more information into fewer qubits than the same number that would be required for classical bits, in principle, it could be a more efficient way to store large amounts of data. However, because there's something called the coherence time of a qubit, which basically means how long is the information stored within a qubit viable before it leaks information to the environment and we can no longer use it for information processing. These coherence times are currently extremely short, extremely short. And so you would not necessarily want to use them for quantum memory as it currently stands. But it's a good question.
How short?
Thanks.
Just curious.
That's a really good question. That's a really good question. Let's see. I'm actually curious what a typical one is.
So these are actually stored as like the state of a hydrogen atom, possibly.
So
How long do you keep that?
So for instance, like photonic quantum computing, they have very long coherence times, but they have other problems. If you use something like a superconducting circuit, for instance, is like the most popular method to implement a quantum computer. The coherence times are really short. I think only like a few microseconds or milliseconds currently. So yeah, not long enough to do anything truly useful. Does that help?
Yeah, no, totally.
Okay, cool.
What's up? I didn't get why is it a block sphere and not a block circle? Because the precession is not really included in the.
So if I think I understand your question correctly, so this is a 2D surface of a sphere, and these vectors can point anywhere on the surface. So this is showing 3 different qubit states at once. Typically you only have one arrow. This is just trying to indicate like it can point in different directions. But because this arrow can point to anywhere on this surface, a sphere is needed to essentially visualize that. You can also visualize it not as a sphere. A lot of people will convert, say like, so a couple of the equations we looked at earlier, you can convert to like polar coordinates or as a function of like two different angles.
Yeah, exactly, because you showed three angles like this, so phi here. Like, does that change, like, is it independent, like the state of your qubit is independent of phi or not? Like,
You can describe it as a state as a function of these two angles. The state of the qubit is not independent of phi. But for instance, it's a good point you bring up. So earlier I showed that any state along the equator, which is just one small subset of quantum states, every single measurement outcome, everything on the equator has a 50-50 chance of being a 0 or a 1. So even though they're not the same quantum state, they have the same measurement outcome, the same probability of having the same measurement outcome. This is kind of the trickiest thing when you first learn quantum computing, is that the information contained in a qubit is not necessarily the information that we can actually access. We can use it, but we can't always know what it was until after we measure it. It's kind of weird.
And it's two-dimensional because there are two probability vectors in there?
Yeah.
Okay.
Maybe you're gonna get to this, but how are these encoded? You encode like a superposition of states.
Yeah, that's a very good question. And we're about to find out.
Okay, great.
Qiskit is an open source software development kit that we use to interface with quantum computers. What you're seeing here is what's known as a quantum circuit. Just a quick overview of what's actually going on here. So there are 3 qubits, qubits 0, 1, and 2, and they are kind of held along these wires, which aren't physical, and they're read from left to right. So these boxes are gates, and this indicates measurement. And you see the arrow that points to this line. This is a classical register. So for every qubit, you also need a classical bit to store the value of the measurement. And so kind of like a circuit, this is somewhat similar to like the classical gate model for computing. First we initialize the qubits, which are initialized in state 0. Then we apply certain logic gates to them, which cause them to interact and change their state. And then we measure them, and we're left with 3 classical bits. So at the end of a quantum computation, you're left with the classical bits. You're not really like afterwards, analyzing qubits. You're analyzing classical bits. So we'll go through how a quantum circuit is built using Qiskit, and we'll also explore how you can generate entanglement, which is one of the core quantum phenomena that quantum computers exploit. So I will now go to this tab. Okay.
So is entanglement essential to the exponential increase in computing power with qubits, or is that separate?
So each individual qubit, in principle can store, 2 to the n complex probability amplitudes, but entanglement allows us to essentially interface 2 qubits together. In quantum computing, we don't think of like each qubit as fully independent. We'll see in this demo that they interact with each other, and entanglement allows us to do things that just have no classical analog whatsoever. But it's definitely, like, in my mind, it's the most interesting and most powerful tool that quantum computing has over classical computing. So this is a Jupyter notebook that I'm happy to share with everyone after this. I developed it in part using something called the Qiskit textbook, which is a really useful online resource that I highly recommend people at any level learning quantum computing. For those unfamiliar with a Jupyter notebook, you can have text boxes and code boxes, and you can run them in the browser. So I want to start by talking about the 3 stages of building a quantum circuit, which is a quantum circuit is basically a recipe that we give to a quantum computer, which it then executes, and then it gives us out the information that we have that we wanted to process, which in principle is useful. Maybe it will never be used. We'll find out. So this is a quantum circuit, and now we're going to start building it up piece by piece. I'm not going to focus too much on the code. I more so want to give you an intuition for like how this actually happens. And run them because it'll be hard to read. So it's so simple. It's deceptively simple. For instance, this is a very, very basic quantum circuit, which initializes 2 qubits. This is a barrier which does nothing, just for visual separation. And then there's measurement on each of the qubits. So you might be wondering, okay, so what do we get from this? Qubits are typically initialized to the 0 state. And so if we apply no logic gates to them whatsoever, we should expect to measure a 0 at the end. Now, mind you, this code can also be run on a real quantum computer through IBM's quantum cloud. However, there's a bit of a queue today, and so we're going to be using a classical ideal simulation. But with changing 1 line of code, you can submit it for free to their quantum computers, which are, some of which are located in Yorktown Heights. So, the first step is actually just establishing the quantum circuit, and we're going to ask for 2 qubits. We're going to measure all the qubits after initializing them, and then we're going to draw it. You can see here a very, very basic quantum circuit, which does not yet include any gates. So it only includes phase 1 and 3, which is initialization and measurement. Okay.
So when does it have a 1 coming out?
Right here?
Yeah.
So this is indicating that qubit 0, after we measure it, the value is stored in classical bit 0. And then the value from qubit 1 is stored in classical bit 1.
Oh, those are labels, not values.
Yeah.
Okay.
Oh my God, that's so important. I should have said that. And I'll send this and feel free to go through it all. It's a little more in depth than we have time for today. Let's simulate this quantum circuit, which again still has no quantum gates in it, but you can measure an initialized qubit just on its own.
So you're expecting 0 and 0.
Correct. Wow, yeah.
But since they're quantum, maybe not, right?
Yeah, so, well, if this was a real quantum computer or a noisy simulator, we would actually expect some of these values to be flipped. Maybe like 10% of them are wrong or something. Because this is an ideal simulation, not actually being run on a real quantum computer, we're getting ideal results. But yes, assuming everything's going according to plan, we should expect 0 and 0. And one day, at least I hope, quantum computers will, even on a real quantum computer, give us 0, 0. So what you can see here is what we discussed earlier. This is a histogram, so pretty useful for trying to comprehend like the probability distribution of the results. And so we ran this experiment 1,024 times, and we found that every single time, both qubits we measured to be in state 0. And so, okay, we've done absolutely nothing to it yet. So that checks.
The real quantum computer would give not 100% as 0, 0 because of like errors of initialization, or is it something in the process after initialization?
So within a quantum computer, there's errors at literally every single stage of it.
Okay.
So initialization can sometimes go wrong, the quantum gates can go wrong, the measurement can go wrong, and unlike with a classical computer, you cannot rely on redundancy, which is basically how we protect classical information now. On a quantum computer, there's something called the no cloning theorem, which means you cannot arbitrarily copy a quantum state. If I have a qubit here, I can't just duplicate it into a separate qubit and copy its state. You can transfer the state to a new qubit, but then the first qubit will lose the state. So because of that, we can't rely on redundancy for error correction.
Because to copy it, you'd have to measure.
Say it again?
Because to copy it, you'd have to measure it.
Exactly.
And then it collapses.
And then it's just nothing again. With something called quantum teleportation, you can actually transfer the state from one to the other. That's outside the scope of this talk. Yeah. So we've not yet applied any quantum logic gates, so why don't we start doing that? So as we discussed earlier, the qubit states are represented with vectors. Logic gates are represented with matrices. Specifically, they're the kind of matrix where if you apply two of them at once to the same vector, you'll get the identity matrix, and so nothing happens, ideally. The most simple gate, which does have a classical analog, is the Pauli X gate. You can see its operation here using bracket notation. So this is the gate. This is the qubit, which is in the 0 state. So this is the matrix representation of the X gate. This is the vector representation of the 0 state. And so, I've not actually done the math for linear algebra in years, but I trust that it leads to this state, which is the 1 state. And so what you can see, what it's doing is it's flipping the 0 state to the 1 state. It would also flip the 1 state to the 0 state. Very basic. This is classical computers do this every second. There's nothing really quantum going on there yet. So you can see here that you can apply the X gate to the circuit that we built before, giving us a new quantum circuit. And now we should expect somewhat different results. So given that I said that it flips the probability amplitude of the 0 state and the 1 state, does anyone have any guess for what we might find in the histogram upon simulating the circuit?
0.
Yes, except for some reason, I'm sure there's a very good reason for it, they reverse the order of the classical bits when they're read out. I literally couldn't tell you why. I have no idea, and I don't like it. So this is the classical bit for qubit 0. This is the bit for qubit 1. So it's 0, 1, not 1, 0. I'm sorry, I don't make the rules. This is how this thing works. If you want, you can flip them afterwards. But you're right. The first qubit, which is this one, is in the 1 state every single time. The second qubit is in the 0 state. Okay, so far we've introduced nothing quantum. Now, let's talk about something that is quantum. This is kind of the most iconic quantum logic gate, in my opinion. It's called the Hadamard gate. This is how we start changing the state of the qubit from something classical to something quantum. So the Hadamard gate, which is represented with this matrix, takes a qubit and puts it into something called a superposition. So if we look at the block sphere from before, if the qubit, which is represented by a vector pointing to the North Pole of the block sphere, if we apply a Hadamard gate to it, we would expect the vector to turn 90 degrees until it represents this state on the equator. So in bracket notation, you might remember that what this is indicating to us is that there's two complex probability amplitudes that are both 1 over square root 2. And so what the Hadamard gate does to the 0 state is that now, upon measurement, we have a 50-50 chance of measuring a 0 or a 1. Before, it was always going to be 0, ideally. Okay, interesting enough. So this is what the circuit diagram would look like for just a Hadamard gate on the first qubit. So again, very, very similar to the circuit beforehand. Does anyone have any guesses for what the histogram might look like now?
1 1/2 0 1.
That is correct. That is correct. This also motivates why we need more than one shot or experimental run of the quantum computer. You can see here that roughly, half the time we're getting 0, 0, roughly half the time we're getting 0, 1. So this is one of the key differences between quantum computers and classical computers. Quantum computers can be probabilistic, whereas classical computers are deterministic. That's really fascinating. I like to think of like a coin flip as not really being probabilistic because it's more a function of the fact that we don't really know what's going on. Like we don't know how hard it's flicked. We don't know like what the air is doing. You could probably train yourself to like flick heads or use a computer to like comprehend before it lands what you're going to measure. With the Hadamard gate, which has been experimentally realized, it is truly probabilistic. It's not that necessarily that we don't know enough. It's that the outcome cannot be known until it's measured. So you get to these like interesting philosophical questions with quantum computing too. Like is determinism real, and you know, is probability real? And it's kind of really exciting even from that perspective. Still, you know, we're not really doing anything super useful.
Can I ask you a question?
Sure.
And I hope somebody explained to you the way that GISS seminars work. Make a 10-minute presentation that lasts 15 minutes.
Yeah.
So in uncertainty quantification, there's things like polynomial chaos, where you have like intrusive and non-intrusive methods for like propagating uncertainty through something, where you try to represent things basically probabilistically, or see what the equations do to that probability. Have people proposed using like quantum computers for similar methods? I have no idea.
So nor do I. That's a great question. I have absolutely no idea.
I'll look into it.
Yeah, and let me know what you find. I would love for anyone who's interested in quantum computing. We could talk more after and so forth. There's a lot of interesting applications that we will not have any time to get to. So the third gate that we'll look at today is called the C0 gate. This is what's known as a 2-qubit gate. So before, you can see that the Hadamard gate is acting on only 1 qubit. The X gate is acting only on 1 qubit. What if we want them to interact in some way? What if we want the state of 1 qubit to depend upon the state of another? Thus enters the C0 gate. So there's a few different representations here. Just bear with me. This is what it looks like in the circuit. There's a control qubit and a target qubit. And depending on the state of the control qubit, we will change the target qubit in some way. This is the matrix representation for it. For instance, there's a few examples here. Essentially, you flip the state of the target qubit if the control qubit is in state 1. If the control qubit is in state 0, you do nothing to the target qubit. So you can see some examples here. You know, before and after, the control is 1, the target is 1, and then so it goes from 1, 0 to 1, 1. 1, 1 becomes 1, 0, whereas 0, 0 will stay as 0, 0. And you know, if we're looking at it in Brockhead notation, you can see that we're swapping the complex probability amplitudes for the 1, 0 or the 1, 1 state. So this is indicating the quantum state of a 2-qubit system. And so that's why within each bracket there are 2 numbers. So for instance, A, B, C, and D, like with a 1-qubit state, these are just complex probabilities. So you know, A could be 1, and B, C, and D could all be 0. And then we'll know every single time we're going to measure the qubit in state 0, 0. The qubits in state 0, 0. Okay. Why on earth would anyone seek to do this? I will try to explain. So here's another example of a quantum circuit. You can see here we're adding an X gate on the first qubit, and then we're doing a CX gate. So this indicates we're using qubit 1 as a control qubit, and qubit 0 as the control qubit, and qubit 1 as the target qubit. And then we're after that applying the X gate to qubit 0 again. This kind of might train you to think in this sort of like left to right sort of wire format. So anyone care to guess? Let's go qubit by qubit. What do you expect qubit 1 to be measured as?
Here.
I hear 0. I hear 1. Those are the only options. So
I think you have to scroll back up to that.
yeah, not yet.
Are they still they're both initialized at 0, 0.
Yes. However, in qubit 0, you'll see that before we use the C0 gate, we're first applying the X gate to qubit 0.
Yes.
Which means that if we're reading from left to right, piece by piece, the control qubit is in state 1 when the C0 gate activates. And so we should expect that qubit 1 will be in state 1 upon measurement, as there's no more gates applied to it. So if there's no more gates being applied, that qubit is totally set in stone. Well,
Flips again.
So the actual answer is 1 0, or 0 1 depending on the order. Sorry for that. The reason being is that quantum logic gates are reversible, and so we've applied 2 X gates to qubit 0. So first it started in 0, we flipped it to 1, we used it as a control qubit in the CNOT gate, and then we flipped it back to 0. But that doesn't undo what happened here. When this was the control qubit, it was able to flip qubit 1. And so, this is one of the powers of quantum computing, is that the gates are all reversible. And so that has a myriad of applications we have no time to get into, actually. So every single time we expect the same result. Okay, so all this culminates in this part of the demo, entanglement. This to me is the most exciting thing that quantum computers can exploit. Essentially, entanglement has to be between 2 or more qubits. It can be any number of qubits higher than 2. So far, all the qubits we've looked at, you can actually separate, the bracket notation or the linear algebra into 2 independent components. For entanglement, you cannot describe each qubit independently. So if you have 2 qubits, there's no way to I can't tell you what's happening with qubit 0, and I can't tell you what's happening with qubit 1. I have to tell you what's happening with both of them. So it's kind of 2 halves of a whole. Interestingly, entanglement can be maintained across vast distances. And so 2 things don't have to be actually in close proximity to maintain their entanglement. To become entangled, they probably have to be in close proximity, but then you can in principle separate them and give them to 2 people, and weird things start happening that really upset Einstein. So
why did you say that to become entangled, that be in close proximity? Why you say that?
So typically, as I understand it, for instance, if we're dealing with 2 photons, typically you generate them at the same time, and the way they're generated creates the entanglement. And so they have to be because they're coming from the same source, they have to be close by while they're being entangled. And as we'll see in the circuit diagram below, the way that you entangle 2 qubits using a CNOT gate, these gates typically are applied over short distances because I think their fidelity is higher that way. So this is the state representation of something called a Bell state, which is kind of the best example of entanglement that we have. So the way you interpret this this equation is, again, the complex probability amplitude is 1/√2 for both of these measurement outcomes. And so what this means is that we have a 50-50 chance of measuring the qubits in states 0, 0, and a 50-50 chance of measuring them in state 1, 1. There's no other options, which means every time you measure this qubit as state, and you get a 0 out, the other qubit will always give you a 0 out. And they don't always have to be the same value. Sometimes they're reversed, and there's many ways things can be entangled. So it's actually very, very simple to entangle 2 qubits together using a quantum computer. This has been done experimentally a myriad of times, and it's using 2 gates that we learned about earlier in the demo, the Hadamard gate and the CNOT gate. This is all you need to do to entangle 2 qubits. First, you put qubit 0 into a superposition, and then you use that qubit, which is in a superposition, as the control qubit for a CNOT gate, which affects qubit 1. And so when qubit 0 was in state 0 or 1, it was a little more clear what a CNOT gate would do. When it's a 0, nothing happens. When it's a 1, something happens. What about when it's in superposition, when it's neither a 0 or 1? Well, you get this.
Right. Because half the time it works and half the time it doesn't.
Yeah, you kind of intuit, roughly half the time this is going to be measured as a 1, half the time it's measured as a 0. You can intuit that roughly half the time. So let's say this is 0, even though this is not really a good way to think about it. If this is 0, heading into the CNOT gate, it will not flip this, and so you'll get 0, 0. If it's a 1, it'll flip it, you get 1, 1. You can't measure here, and so that example isn't really poignant. But the reason why this matters so much is that, let's say I create an entangled pair of qubits and I give one to a friend of mine, and then we go across, and then we live across the country from each other. If I measure my qubit instantly, my friend's qubit will also be determined to be in state 0, even though we are spread across vast distances. That does not violate the speed of light for various reasons, but essentially, I can send information to you across incredibly vast distances without doing anything in between us. Just the entanglement of the two qubits alone can be used to transmit information with no physical link between them, through vacuum, through anything. And so this is used in many, many quantum algorithms, and also is just kind of interesting on its own. So yes, that is a very, very quick intro to how Qiskit works. All of these quantum circuits can be run on quantum computers through IBM and other companies fairly easily. You basically just change what backend they're working on. And it's very exciting, it's very fun. I really encourage you to play around with it. And I would encourage you to use the Qiskit textbook if you want to learn how to use Qiskit, which is, in my opinion, the quantum SDK with the best community surrounding it. So yeah, there's a couple closing points I want to make in the last couple seconds we have. Does anyone have any questions about entanglement? Last resource we looked at.
Is there like a limit on the distance?
In principle, no. Not necessarily. Like engineering problems, like maintaining the entanglement. I'm sure something has to be done to like not disturb the qubit in some way. You have to keep it very isolated, but the distance is not really the important fact. The important part. It's just keeping it kind of secure and safe.
And that's after the entanglement has happened.
Correct.
Okay.
There was a presentation I got 2 years ago by a company that was doing secure transmissions this way.
Yeah.
And I remember reading in the Hacker News about a month later they were hacked. Their system was cracked.
Yeah.
And the way they did it was by bombarding it with additional radiation to cause it to decohere.
Yeah.
And then it became classic way after that.
Yeah.
So, but it was before that, it was sort of unbreakable because if you fiddle with it, then it decoheres and then the information is gone. So you've been hacked.
Yeah, this is one of like the core crypto applications of quantum computing to cryptography.
Yeah.
Because measuring the quantum state changes it in a way that you can instantly detect. If someone is eavesdropping upon a secure line of communication, there will be certain hallmarks in the resulting data that will indicate that you have been eavesdropped upon.
Yeah.
Because in quantum physics, measuring or observing a system changes it fundamentally in a way that is untrue classically. So this has a million applications that are really, really fascinating. Yeah. So I just wanted to finish up in the 100 seconds we have left.
A little bit over.
Okay.
That's okay.
Yeah. I won't be mad if anyone has to leave. So yeah, with what we just went through, in principle, any of you could now build a quantum circuit and execute a huge amount of quantum algorithms as long as you follow the instructions on how to build the circuit. But even just those 3 gates, the X gate, the Hadamard gate, and the CNOT gate, can be used for a profound amount of quantum computing. So just to give you a sense of like how many qubits we're working with, I think IBM's biggest quantum computer only has 433 qubits. We would need tens of thousands of qubits for anything really useful. There's also a distinction between what's known as a logical qubit and a physical qubit, because correcting errors typically requires some kind of redundancy. It requires many physical qubits for each logical qubit. A logical qubit is basically like how with classical bits we only really have logical classical bits. With quantum bits, you have to have this sort of redundancy built in, which increases the overhead hugely. So this is not even 433 useful qubits. It's maybe a fourth of that. everyone's aiming for like 1 million or 100,000 qubits by the end of the decade. So, over time you can see, 20 years ago we have 2 or 3 qubits with which you can do nothing. In 2019 we have 128. You can see the kind of the rate which is growing. I'm a little skeptical that it's going to grow at the same rate. I think there's major engineering problems that are going to stand in the way of quantum computing happening at the end of this decade. I would say if it is going to happen at all, it would be more like in 20 years. But that's a more conservative estimate because I don't like hype. Ultimately, they're not really intended to replace classical computers or work alongside them. There are certain problems that quantum computers are probably not worth using for. And there's also a whole class of algorithms that use quantum computers and classical computers in tandem, where you adjust the quantum circuit based on classical computations, and it's a sort of feedback loop. So there's some really exciting applications that are worth mentioning. In my opinion, the most useful case for a quantum computer is chemistry and physics simulation. Again, when we're simulating, let's say, like a new drug or a molecule, it's so hard to do that classically because every single new qubit or quantum element you add, you have to keep track of twice as many variables. And so it really isn't feasible to do it classically. Certainly not classically and quickly and accurately. You have to make all these assumptions and use supercomputers, and major problems ensue. Whereas with a quantum computer, simulating, say like the ground state of a certain, molecule or chemical reaction is in principle much easier if you have enough qubits. A really, really exciting thing people talk about is nitrogen fixation, which, as I understand it, basically gives us all of our fertilizer in the world. It's using the Haber-Bosch process, which is 2 to 3% of our CO2 emissions globally every year. So, if we're interested in cutting emissions, quantum computers could help with that, because we could, in principle, better understand the chemical reaction that leads to nitrogen fixation. Unclear. Also, people talk a lot about new materials, and so much about material science is about simulating really inefficiently quantum properties. Maybe we could create more efficient batteries. And so you can see there's a lot of exciting applications that could really help us. People also talk about weather forecasting and machine learning and AI and cryptography. There's a lot of potential applications. I'm sure some people are interested in climate modeling, of course, using quantum computers. That is a whole other day if you want to keep talking about it. There are some initiatives around the world, maybe like a handful, that are trying to explore the connection between quantum computing and climate modeling. Ultimately, climate models deal with simulating a lot of nonlinear effects. Quantum physics is innately a linear theory, and so there are some challenges there. But because a lot of this involves very complicated systems, a lot of data, in principle, it's worth looking into. But basically, no one has really looked into this that much. No one's really tried to do it yet. So if you're interested, this is sort of out there. I think someone should maybe do like a PhD thesis on it or something. So yeah, thanks so much for listening. Hope that made any sense. I'm not an expert, so just trying to drum up some interest. And yeah, if you have any questions, you can email me. Yeah, thank you.
So we have gone a little over time. So if you need to leave, please feel free to. Tyler, I don't know if you need to leave right now. Okay, so if you guys want to hang out and keep discussing, you can. I know we have Kostas has raised his hand again online, so if you want to unmute yourself.
Tyler, thanks a lot. That was very nice.
Thank you.
I wanted to ask something that goes on in parallel in classical computing, which is GPU acceleration. Is this somehow part of the game? I mean, this will evolve in the future as well, right?
So I don't know much about GPU acceleration. Could you explain what that means?
Yeah, so the idea is that the GPUs which are the graphics cards that the computers have, are much more efficient for certain types of problems than the CPUs are. So supercomputers, including Discover, I think, are now starting to offer some GPUs for computing And I've heard that there are some models that are trying to work on using those GPUs to accelerate things further. So the idea is that if you have something that contains math but not logic, you can do it very, very efficiently in GPUs. So if you have a massively nested loop, you can do it in GPUs in a fraction of a second, while it will take forever on a classical CPU. But if you start implementing if statements within those do loops, then the GPU will just collapse. It will never finish. You know, things like these. So it's an evolving thing. So yeah, if you're not familiar, I guess you cannot answer, but I was wondering.
Well, Costas, I know the answer to this, because the reason why the GPUs are better is that's an architectural engineering thing. It doesn't have to do with the fundamental nature of the computing. It's that GPUs were engineered to throw a lot of math at the graphics. I mean, to compute the graphics. So they do polygon math really quickly. And they've evolved that way for commercial pressures, not because there's anything special about GPUs. While the CPUs have evolved also for commercial pressures to not do that and have a logic instead. So that's sort of that's like an economic side effect. It's not really a architecture or design effect.
Right, but that does accelerate math at the end, right?
It doesn't, yeah, it can, so GPUs can do certain kinds of math much faster than CPUs, but that's just because they've been engineered to do that. It's not a different paradigm.
Yes, of course, of course. I mean, it's still bits of zeros and ones, of course.
Yeah, exactly. So that's true, but I think the quantum stuff cuts sort of sideways across it.
Yeah. My question was mostly whether, when speaking about classical computers, we are taking into account that maybe in the probably near future, the part of the math will be done in GPUs, so the classical computers might accelerate their performance faster than what we envision right now with CPUs alone.
Yeah, it's true. It changes the category of problems that are computable.
Right.
Yeah, I would expect that the first applications of quantum computing that are useful will be within a hybrid architecture of CPUs, GPUs, and QPUs, as they're sometimes called. Very likely, certain computations will be offloaded to quantum computers, and then the results of that will be used by CPUs and GPUs.
I have a quick question for you. And this is, I'm sure, a loaded question, but like, what do we/you know about the physical processes of entanglement? Like, do we know how it works out, or we just know because we've measured it?
Yeah, it's very much a lot of physicists take like an instrumentalization approach or instrumentalism approach, meaning like what we know about it is what we can measure,
Right.
and like the actual ontology of what's going on.
Beyond our current understanding of.
I'm sure many people have a lot of compelling ideas about it. I don't understand them.
Right.
So if I found out, maybe I want a Nobel Prize. I don't know.
Right.
I'll let you know. If I find out, I'll let you know.
Okay, thanks. Same.
Thank you. Thank you.
Okay, I think we'll cut it off there. Thank you so much for staying a little bit later.
Thank you for having me.
Maybe like the five of us can give you another round of applause. That was really great.
Thank you. I really appreciate it. I really appreciate it.